Hello! In this video, we are going to talk about trigonometric identities and how to solve proofs involving trigonometric identities. So we're going to look at Pythagorean identities, such that sine squared plus cos squared equals 1. We're going to look at quotient identities, such that tan theta equals sine theta over cos theta. And we're also going to look at the reciprocal identities, which are telling us that cosecant, secant, and cotan are the inverse of sine, cos, and tan, respectively. So I'd like to bring your attention to this unit circle over here. So our unit circle is basically when we have a circle around our axis, our x-axis and our y-axis, and that circle has a radius that is equal to 1. So for that circle, for any point all the way along that circle, the angle between my initial arm, which is the x, positive x direction, and my terminal arm, which is the radius of that circle, will have an angle theta, and then the x value of that point along the rim of the circle, well, this x value will just equal the cosine of theta, right? Because the radius is 1, and if you remember, cosine is adjacent over hypotenuse, so the adjacent is my x over the hypotenuse, which is 1, so x over 1 is just x equals cos theta. So, and over here, our y value similarly is just going to be equal to sine theta. So my opposite is my y value, my adjacent is my x value, my opposite is my y value, and my hypotenuse is the radius. So if I wanted to figure out what tan is, well, tan theta is the opposite over the adjacent, which is equal to y over x, or sine theta over cos theta. So that is where my quotient identity comes from, this idea that tan theta equals sine theta over cos theta. And that is one of the three identities that we use quite often in solving proofs of trigonometric identities. Something else that we might want to do with this right angle triangle is use Pythagorean's theorem. If we wanted to figure out what r squared was, right? R squared is just 1 times 1, which equals 1. But using Pythagorean theorem, I know that that is equal to the adjacent, or one of my legs over here, which is x squared, and I'm going to add my opposite, which is y squared, right? So x squared plus y squared will equal my radius squared. Well, I already know my radius is 1, and I know that x is cosine, so cosine squared plus y is actually also sine theta, so cosine squared plus sine squared theta just equals 1. And that is my Pythagorean identity over here. That's one of the most often ones we use. And the other forms of Pythagorean identities are basically just rewritten versions of that. So if I bring the cosine over to the other side, I have sine squared theta equals 1 minus cos squared theta. And similarly, cos squared theta is going to equal 1 minus sine squared theta. The reciprocal identities basically have to do with this idea that cosecant theta, well, that's just equal to the hypotenuse over the opposite. And since sine theta is equal to the opposite over the hypotenuse, well, that means that I'm just flipping sides. So that means that cosecant theta is equal to just 1 over sine theta. So the reciprocal identities are essentially just the inverse of sine theta, cos theta, and tan theta. So similarly, since tan theta can be expressed in terms of sine and cos, that means that cotan can also be expressed in terms of cos and sine. So if tan theta is just sine over cos, cotan is going to be cos over sine. Okay, so let's talk about how we can actually use these identities when proving equations that have trig functions in them. So what I have for you is 4 strategies that can help you with your trig identity proofs. The first one is to move from a more complex statement to a more simple one. So sometimes you are going to have to work on both the left side and the right side of an equation at the same time in order to get eventually the same expression. But generally, what we're going for is to have a more simple expression. So what I mean by that is over here in our example, I have cos squared x equals 1 minus sine x times 1 plus sine x. So on the left side of my equal sign, I have just one statement. And that definitely is more simple than on the right side where I have 2 statements in brackets here multiplied by 2 statements in brackets. So it's a lot easier for us to start with something more complex and break it down. So we're going to start with the right side of our equal sign. And I'm only focusing on the 1 minus sine x times the 1 plus sine x. And what I'm going to do here is expand it using the FOIL method. So 1 minus sine x, so first I'm going to be multiplying the first terms, so 1 times 1 is just 1, and then I'm multiplying the outside terms. 1 times positive sine x is plus sine x, then I'm multiplying my inside terms, I get negative sine x, and then I multiply my last terms, which is negative sine x times positive sine x, I get minus sine squared x. So you'll notice that our middle terms are actually canceling out because positive sine x minus sine x is just 0. So I'm going to write 1 minus sine squared x, and that actually already looks just like one of my identities. That looks just like my Pythagorean identity over here. 1 minus sine squared x is just equal to cos squared x. So I'm going to replace 1 minus sine squared x with cos squared x. And hey, that's exactly the same as my left side. So once my right side equals my left side, then I'm done. And that means that the equation was proved. Okay, second trick is we're going to express our functions in terms of sine x and cos x as much as possible. So in this example, I have cos theta times tan theta equals sine theta. And so if I'm saying sine of x and cos of x, that means that as long as the term that's after sine and cos is the same, then we can treat it like a sine x and a cos x. So here I have cos theta and tan theta and sine theta. And so I'm going to just treat all of those thetas as if they were x's as well. On the left side, I have cos theta, tan theta. On the right side, I have sine theta. I want to make sure everything's in terms of sine and cos. And I know that I can use the quotient identity over here to turn a tan into a sine and a cos. So I'm going to start with my left side of this equation. So the left side over here is equal to cos theta times tan theta. And I'm going to replace tan theta using my quotient identity with sine theta over cos theta. So when I'm multiplying cos theta times something that's being divided by cos theta, then my cos theta can actually cancel out. And I'm left with just sine theta by itself. And that's already equal to the right side, so I am done proving that identity. Okay, moving on. I've got my third strategy, which is to look for squares and use the Pythagorean identities whenever possible. So here in my example, I have sine to the 6th theta equals 1 minus cos squared theta cubed. So sine to the 6 theta, that is just one term. So I'm going to start with the more complicated one that has two terms, and that's being cubed. So I'm going to start with my right side over here, and that's just equal to 1 minus cos squared theta cubed. And I'm being told to look for squares and use the Pythagorean identities. So when I'm looking for squares and using the Pythagorean identities, oh, well, inside my brackets, I have 1 minus cos squared theta, and it looks like I can replace that with a sine squared theta. So I'm going to replace my 1 minus cos squared theta with a sine squared theta. And all of that is cubed. And I remember back from the exponents unit that if I have an exponent to a power of another exponent, what I need to do is multiply those exponents. So I'm going to have sine to the power of 2 times 3 theta, and that means it's going to end up being sine to the 6 theta. And look at that, that's actually the same as my left side. So my right side equals my left side, and I'm done. My fourth trick for you guys is to use algebraic manipulations. So this is kind of meaning that almost everything we've learned to this point, such as distribution, factoring, creating common denominators, these are all different methods that we can use to manipulate algebraic expressions. So these will also come in handy when you are needing to prove things, right? So over here I have an example. On the left side I have sine theta plus cos theta squared plus sine theta minus cos theta squared, and that is all equal to 2. So I'm going to start with the more complicated side, which is my left side, and I'm going to manipulate this expression in order to make it equal to the right side. So I'm going to see, can I do any distribution? Well, yes, I can. I've got sine theta plus cos theta, and that's all squared, and sine theta minus cos theta is also squared. So I'm going to go ahead and use my expanding knowledge. So sine theta plus cos theta squared means I'm multiplying it by itself. And similarly, sine theta minus cos theta is also squared, so I'm also multiplying it by itself. So when I do that, I'm using the FOIL method once again. So sine theta times sine theta is sine squared theta. Sine theta times cos theta is sine theta cos theta. And then the insides are cos theta times sine theta. So I'm going to also write that as sine theta cos theta. Just a side note, sine theta cos theta is the same thing as cos theta sine theta, right? It doesn't really matter if you're multiplying 2 times 3 or 3 times 2. They both end up equaling 6. So the same idea is over here. If you're multiplying sine by cos, that's the same as having cos times sine. Doesn't matter which one's first. And then cos theta times cos theta is cos squared theta. And then I'm going to, so that one is all done, and then now I'm going to move on to the sine theta minus cos theta. So sine theta times sine theta is again sine squared theta. Sine theta times minus cos theta is minus sine theta cos theta. I'm going to run out of room here, so I'm going to go over to the next line. Negative cos theta times sine theta is once again another minus sine theta cos theta. And last but not least, negative cos theta times negative cos theta is another positive cos squared theta. So my next step is to just group everything together. So I see that there's a sine squared theta over here and another sine squared theta over here. So I'm going to write those as 2 sine squared theta. And then I see that there's a sine theta cos theta over here, a sine theta cos theta over here, and then a minus sine theta cos theta, and another minus sine theta cos theta. So all of these are canceling each other out. And then I'm left with a cos squared theta over here and a cos squared theta over here. So I'm going to write those together as positive 2 cos squared theta. Okay, so now I have 2 sine squared theta plus 2 cos squared theta. I've expanded everything, so I can't really do any more distribution, but then I ask myself, can I factor? And yes, I can. Both of these terms have a 2 in common. So I'm going to factor out the 2, and I'm left with, in brackets, just sine squared theta plus cos squared theta. And if you remember from trick number 3, we are supposed to look for Pythagorean identities whenever possible. So I remember that in my Pythagorean identity, says that sine squared theta plus cos squared theta is equal to 1. So I can replace those brackets with 1. So instead of writing sine squared theta plus cos squared theta, I know that all of that is just equal to 1. So 2 times 1 is just 2. And that is equal to my right side. So I have proven this identity. Okay, so in the next video, I'm going to show you some more examples of how we can simplify sine and cos functions or expressions that use sine and cos functions, and also some more examples on how we can prove identities.